what we will do today, we will do 1 hour and take break and come back and do another hour. So instead of actually 2 hours straight, okay? Okay. The agenda for today will be workload. We will talk about the workload characterization. The problem, if we have time, we will actually formulate a couple of problems and discuss a simple example of characterization. What workload characterization is, what workload we want to characterize, and present some workload characterization. Now, what I present today is actually used in these papers. Now, in our area, IEEE Transaction Parallel Distributed System is the top journal. So everything I'm showing you today about modeling is used in this paper. It is also used in this paper. Also, this guy uses it a lot. So it is really what is being used to produce or characterization of workload models. Okay? So I hope by the end I will be able to convince you that what many people simply randomly choose values for workloads is not actually the workload, but there is a mechanism and a way to model the execution environment, that's cloud computing, as well as the workload model. Okay. Now, in a production environment, workloads appear differently. So if you are modeling a workload, a real environment, you see a lot of different workloads. It's not really one workload. And we see a variety of workloads with a variety of resource requirements. And some are long-lived, some are short-lived. There are a number of different probability distributions that are used to characterize all these features of workloads and jobs. I will use workload and job interchangeably, but task is part of workload, part of a job. So a job is one composite workload, and each job can have multiple tasks. So if you take a matrix multiplication application, it is a job. But if you start multiplying, if you give one row by one column to one particular virtual machine or physical machine, that becomes a task because it's part of the overall job. So when I talk about job, I mean the application itself. When I talk about tasks, I mean about the part or sub-problem or sub-task of the job. Okay? Now, depending on, as I said, in real environment, the system receives many different applications or many different workloads. Web service requests are workloads. The matrix multiplication is another workload. And transaction, database, scientific applications, all these are different types of workloads. And each one of these classes of workloads bring different challenges to particularly the scheduling or the resource provisioning algorithm. But they actually impose more on the environment. So the execution environment is the one that gets affected by different workloads. These workloads actually compete for resources. And each competition brings different challenges to the system designers, particularly to the middleware and resource provisioning algorithm designers. And so some of them actually have significant impact, and others have less impact. But it is very, very difficult to choose which one of these features of applications to choose. At some point, I was actually trying to use machine learning algorithm to select the most important features of applications. But I gave up at after a lot of trial, because it's not all applications don't bring all features. Some applications bring just CPU, some are data intensive, some are I/O intensive. So when these come together, you can't actually pick and choose which features are the best. So when you pick I/O, then the communication there becomes bottleneck. When you pick memory usage as the most important feature, the other one creeps up. So it became very, very difficult, but it's still an open issue there. If somebody is interested in exploring this idea of choosing appropriate features of a job before scheduling. Okay, so now we simply model or use application as it is. We don't say which of these features is good, particularly if we have multiple workloads that interact and compete for resources. Now, we are here as resource provisioning people because of this competition. This competition is very, very important to us. These competitions not only come not always come at the same time, but sometimes they come and sometimes they don't. And we want to also maximize the resources, the utilization of resources. Now, the overall goal is to ensure that there are performance metrics, which I'll talk about in the second half of the lecture, which then, if we get time tomorrow, or if we get time today or tomorrow, we will use those metrics to properly formulate a resource requirement or scheduling problem statement in using mathematical, or at least form of mathematical formulation of the problem. Okay. Now, what is workload, or what's a job? Workload of a system can be defined as a set of all inputs that the system receives from its environment during any given period of time. So, as I said, workload arrival fluctuates. If you look at when we did clusters, lunchtime was busy because, especially in university, many students check their emails, try to do assignments, or during the assignment is busy, and in the evening it is just dead, almost zero usage. So that is what I mean during a given period. It's not consistently busy, even though that is what cloud computing wants to use to make the system always busy. But making the system busy all the time, you also pay for energy, which actually you need to minimize. And also making the system too much busy will lead to a lot of failures of the system, because it can overheat, or it can actually, it couldn't handle workload, and it simply starts returning garbage or incorrect results. And these failures can cascade from one node to another and lead to a problem. So when we try to optimize, we are not actually trying to overload the system, but to really come up with some sort of fine level of usage of these resources. Now, these people are submitting a variety of jobs or workloads to the system, and there is a virtual machine manager sitting here that actually takes the jobs and maps to these virtual machines, and then these virtual machines are mapped to the physical machines. In cloud computing, you don't actually get to see the physical machines. You subscribe to virtual machines in certain sizes, small, medium, large, and so forth. And then these are actually in many systems. You have some, they already created and sit in a pool, and you rent it from the pool. Different sizes, but they are there. Now, we need to actually look at, when we do resource provisioning, there are two types of workload, static workloads. These are, sometimes we call them as batch. I'll show you, I'll talk about it later on. They actually come, execute, finish, and go. So the system will be busy during that time. So we say it is a static workload. This is what many people model, particularly in research environment. When we do research, we only do this system. We have some jobs, run it, finish, gone. It is static. We actually rarely model the dynamicity of the system. So when we talk about dynamic environment or dynamic workload, we submit jobs, but jobs arrive to the system, and the workload dynamically changes. Not only the workload types in terms of batch, interreactive, and sometimes also high throughput applications, but the system also dynamically changes, because now the resources will be shared more, and there is no way you can actually determine pre-hand, right? If it is static, we know. We can actually do a simplified system model. But if it's dynamic, now it becomes a bit more difficult. You don't anticipate, you can predict based on the historical previous executions, you can predict almost accurately the next 2-3 hours of what's going to happen. But this is prediction. This is another level of work, which is being done in many areas also, many scheduling algorithms we want to predict in a dynamic environment. I have seen people doing it in a static environment. It is useless. In a static environment, you do and finish. The challenge, if anybody is working in resource management, is how to predict in the dynamic environment. Why these things keep coming? Okay, so if you have any questions, you can stop me and ask me. No, the small thing is coming up now. Okay. Here are sample applications that, if you do it in a dynamic environment, creates problem for resource provisioning, SLA violations, and quality of service maintenance. All these things get affected if you have a combination of these jobs. As you can see, this combination of jobs can be looked at from demand volume. As you go that way, the demand increases. At this level, taxes of office tools, very low demanding. But as you go up in there, as you can see, high performance engineering applications take a lot of crunching to do. So the demand goes that way. So if you developing a scheduling algorithm or resource management for this, then it will not work for this. Your whole system becomes out of control. So you need to know that there are systems, there are applications that span from few seconds to even few days. Okay, now if you look at some of the applications here for weather prediction applications, they actually, for tomorrow, they are crunching it now. After 24 hours, it's useless because tomorrow they announcing it, right? So it is a lot of CPU intensive and data intensive applications. You can also go up, okay? This really always similar. They don't vary. If you look at applications, if in the office environment, if they're actually doing Excel spreadsheet entering, it's always the same, right? If it's database entry or querying of the database, it's always the same. Now, it doesn't have much variability. But as you go up, it changes. Now, if you take web services, sometimes they come in bursts, what we call bursts. They come boom. And then sometimes they don't. So and sometimes they're small, and sometimes they're very big. So the applications or the workloads always shows demand and variability. So the challenge for us is then how to actually model this. In particular, nowadays you can see social networking is there, big data analytics is there, and games are there. Here, disaster prediction, and also here, epidemic simulations, some statistics here, a lot of applications. These are some of the applications that you can see nowadays in cloud environment. So now, the typical, as I said, most people actually work with batch workloads. Batch workloads have two different meanings. Typically, they tend to process huge volume of data. Okay, so applications that actually take a lot of time, a lot of data, like weather data, because the weather data comes from sensors, from other sources, and they have to actually crunch all this data. They're big, they batch, and they are done actually most of the time in the background. They don't require interactive or reading data from the end users. They always have access to everything. Very big. Particularly those people who model, I know he's modeling storage management. Batch is the one that actually kill, and IO intensive applications are the ones that matter in terms of storage management and energy consumptions. Now the other batch workloads are workloads that come at the same time. So all of them come at 0, 0, 0 time. So arrival time is 0, we call them batch. Even if they're variable, they all come at the same time. And because they come at the same time, it's easy for us to design a scheduling algorithm for them, or to design resource provisioning, because we know them, right? All of them came at the same time. But if one comes and one comes later, and small comes later, it becomes difficult. That is what variability I'm talking about. So if a big job comes, and then 3 small jobs follow this big job, these three small jobs have absolutely no impact on the response time of this big job. If you put it to wait, which one will you do? If you put the big one, the small ones have to wait until tomorrow. So these are the challenges that you face with dynamic environment. But batch environment, because they all came together, I know that they have no impact on the execution of the bigger one. I can actually schedule them and finish. So batch jobs that actually run in the background don't really have that much impact, because they always run in the background. When the system is ready, they will get up and run. But batch that actually we say they all arrive, we make a simple assumption that they all arrive at the same time, and then we can run it. They don't actually reflect the real environment. So when we model, we want to model real environment. To start with is good. You can actually see what happens as a benchmark. I always do first batch scheduling, then convert it into dynamic scheduling. So the batch experiment will give me at least to benchmark with. This is the best case scenario. And then if the dynamism in there, I will see how much I'm off from these best case scenarios. Then you compare with another different algorithm. There are two other workloads that we actually need to model. High performance workloads, as I say, where the prediction application is very good, example of high performance workload, and high throughput workloads. Each of these bring different demands in terms of now, the interesting difference between these two applications is that the high throughput applications, you start with small data. So you say, for example, you use the same applications, and then you have, say, 4 tasks, but you start them with small data. If they do correctly return the result, then you increase the data. You keep increasing. So that is the difference from high performance computing. The applications like weather prediction, where you actually need the result at the same time. You give the whole data to the tasks at the same time, and you say you will get the result, the good result. So example of high throughput workloads are different patient data in large scale biomedical trials. So you give small data first, small patient data, you try that. Different parts of genome or protein sequencing in bioinformatics applications, different random numbers in simulations, different model parameters in sample simulations or explorations of parameter space. So the parameter space you want to explore, you start with small, and then you increase the space. That is what we call high throughput workloads. Now, you can actually do this if you want to. You can do in real life, or you can actually model any one of these. Bag of tasks. This is another commonly used workloads. Now, this is not bag of tasks, okay? Bag of tasks are tasks, application has tasks. These tasks are all independent. Okay, they can run in any random fashion. No, in this case, if you see, this task has to run before this. right? Because the output of this will go there. In bag of tasks, there is no dependency. You have a bunch of tasks, you submit it to the system, it run in any order and come back to you. Okay, so this is another common. This is another common applications that we actually use in scheduling and resource management systems. I know that at least 3 people yesterday talked to me about their paper being rejected because of this kind of thing. The reason, as I told you yesterday, is because you're not modeling them. Yes, you're using bag of tasks, but you actually don't model them properly. You can't actually simply say because they can execute anytime, anywhere, you assign them whatever value you want. That's not actually correct. You need to model real life environment as well as real applications. So if you want to use bag of tasks in your paper, take a matrix multiplication. And that matrix model, that matrix multiplication, that will actually allow you to see the bag of task applications and tasks, okay? This is example of bag of tasks, parameter sweeps. This is really very big applications and comprehensive, possibly exhaustive investigations. Raj Kumar actually did PhD on this one. This is what he used, and they even developed a system that was commercialized. As I said, it's bag of task, and they can execute anytime, at any moment, no dependency, no dynamicity. Everything is actually, remember the static workload that I talked about? That is exactly what this is. Very useful in engineering, simulation, and in science. A lot of these parameter sweeps are used in engineering applications and science. Again, you see, when you talk about bag of tasks, you can actually simulate this, okay? Don't simply say, this is my workload, this is my task. Monte Carlo simulation is another example of bag of tasks. And the simulation with random elements, fixed time, yet limited inaccuracies, very useful in engineering, and simulation-based science again. Many other types of batch processing are also examples of this, such as periodic computations, cycles scavenging, applications that actually simply go around and see if your laptop is just doing nothing, they will actually use it, and so forth. Very useful to automate operations and reduce wastes. These are some of the bag of task applications that are used. Now, there are systems that are still useful. Most of these systems are developed during the cluster computing era, which now became cloud computing systems. This is very difficult to model and to use, but it is also widely used in scientific applications and also even non-scientific applications. Nowadays, they are used in social networks and social sciences and so forth. So this, one of my PhD students completed in this recently, Maslina. These are some of the applications you can see here in workflow. This is the IoT applications where a lot of data is being, here is the entire cluster data center where you have analytics engines that perform data analytics, visualization engine that allow the healthcare providers to visualize the data, the execution of the data, and there are applications that can actually subscribe to the data collected by sensors through pull and push, and then this data can come from patients. It can also come from vehicles. You can model, you can do these many IoT applications here. Okay? Okay, now web workload. It is actually an example of interreactive workload. Web workloads tend to be very, very small. Look at the CPU, this one, 0.0095 second. Very small, very, the response time they're expecting is very quick. But there are a lot of them in cloud environment. They create a problem called one of the basic characteristics is the burstness of the web workload. And heavy tailor distribution is basically what this says is that there are a lot of jobs that need small execution but interleaved with some few jobs that require a lot of resources. Okay? Now, we have these workloads. We have the environment. Now, we want to do the performance analysis. There are three ways we can do performance analysis of our workload in our environment. One is use actual workload, actual jobs. So the simple one, as I told you, is use matrix multiplication. But even if you do that, you need to divide the data set, the matrix, into 3 or 4, whatever you want, and then pass it on to different virtual machines. Now, you cannot actually get all the time the same result if you use a real applications. So every time you run, you actually can get different answers. But you get the real working environment of the system. That is fine. But most of the time, you don't have the resources. Okay, if you have a very large applications that needs 1,000 servers, you don't have that resource. What would you do? You can't actually use the actual environment. Now, another performance modeling or performance evaluation of a system or resource provisioning is using trace. So this trace is actually collected by people. In fact, this person, Abawajy, one of my PhD graduate, collected failure trace from the 5,000, I think, the European cluster computing, 5,000 nodes. He collected a lot of traces, and this is openly available. These traces actually show you when machine failed, how long it stayed up, and in fact, sometimes also you can see when one machine failed, the failure cascades to many other machines. Now, The problem with trace-based simulation is it captures certain instances of that machine at that particular moment. So application is running, and we collect data about these applications on that. Now, so this, say for example, if you are running on 64 nodes, but you want an application to run on 20 nodes, what do you do with the trace? How do you downgrade it? You have the trace. The trace data is, it gives you what this application was running on 120, and it accessed this, it accessed that, it accessed this. Now you actually use that to do the performance analysis. But if you want to downgrade it, it's very difficult. Collecting itself is very, very time consuming, very, very difficult. You need to actually know the system very well to collect it. Even though nowadays there are software that allow you to collect it much easily, but still very time consuming, tedious work. So what do? We go to the third one. We can actually use the trace and use the observation of the system, what the system actually returns and what the system does, and model the environment. Okay, that is what the cloud sim tried to do. It actually tried to simulate the cloud environment and the workload with what we call cloudlets. But now what you have in Cloud Sim, if you see, if anyone looked at it, it's what I call batches, right? So all the tasks came at the same time, and always you can see that. That's what is running. But we want to change that. We want to actually make them different, okay? So, but how do we do that? Workload modeling is used to generate syntactic workloads. So instead of simply saying my workload, my job is takes 20 minutes to complete in your paper, you actually need to explain how you generate your syntactic workload. And this syntactic workload, as you can see, oh, it's gone. In next slide, I will show you. We can use this framework. Okay, so to generate syntactic workload based on real-life job execution observations. The observations can come from the traces. Okay, you start with many traces are collected every day. Every big organization is collect traces in log files. By just looking at log files, there are a lot of researchers who are just interested in modeling these workloads from the traces. They have put up a lot of information, the distribution of the jobs, the arrival time, the inter-arrival time, the execution, and all of those. We can do that. If you look at what really happened now in cloud environment, this is what happened. And end users will actually submit information on workload. Okay? So this information can include, I want to use to run this job, and use 2 small, 1 large virtual machine, but I want to pay it in Indian rupees, and I want to receive the result by tomorrow morning. So these are the kind of descriptions you can submit. If you want to model this environment, then you describe, you get the workload here, and quality of service is basically I want this job to be finished by tomorrow lunchtime, something like this, okay? workload, you have to have a workload generator that takes the workload description and produce the jobs, different jobs that actually mimics the real workload. So this workload will generate, workload generator will give you a set of jobs. And these jobs will be sent to workload submission, run, and once you get the workload submission, then this can be actually done before you submit or at the time of submission, depending on the type of system you have. Now, I will talk about service level agreement negotiation. So you negotiate with the clients, okay? So how to achieve this service level agreement? This in itself is another big area. You negotiate the quality of service, the payment method, the results, the violation of service level agreements, and all this has to be negotiated. Okay? As it is now, it is just like, as I said, you simply sort of, you tick. Did you read this 20 pages of service level agreement with your phone service provider? No, because you simply said, yes, this is the kind of work that's existing now. Okay, so what happened? Once you submit, the application runs in here, right? So you get the output, the results. As a user, you analyze the results, you produce the graph. So this is basically what you need to capture when you do research, especially when you model workload and the environment here. So even though I put two components of the cloud computing, this component is very important, always goes with SLA to ensure that violation can't occur or minimize the violations. So what consolidation will do is that it can actually move some of virtual machines from heavy loaded or underloaded machines to appropriate physical machines. So if you want to minimize power, you can actually use consolidation approach. If you want to also load balance, you use this consolidation component. You also need to use it to ensure that service level agreement is not very much violated or minimized. But there are many components depending on what we do that we build in there. Is that clear? Any question? No? Okay. Okay. This is the users, end users. Do you see it?
No.
No, huh? So here it says end user. This part is the real environment. This part is the model. Okay? So end user submits application. They know their application. Right? And then that is actual work, actual job. And then this is the cloud environment. This actual job runs in. And this is the performance that we want to measure. The same here, we model what this guy is giving, right? This is end user, but this is the model. We model, we act like an end user here. Okay? Sometimes we call these brokers. Now, this creates the syntactic workload following this, okay? And you use sort of cloud sim or anything that you develop, and then you performance. So what I am saying is that the syntactic workload that you create must reflect the real world in every aspect. At least must align to real world, looks like real world applications. And the environment that you use also must be very closely aligned with the environment that this application running. Finally, your result also must be close. It should not be off by a lot of degrees. It should track very well the real output. Even though, as I said, this is very difficult. If you repeat, you don't get the same result. But doing this allows you to repeat the same experiment many times and take the average and see. This will not allow you to repeat these experiments many times. Every time you run, it's very expensive. You load the system, you actually get different results depending on what is also running there. But at the end of the day, we want to make this very much aligned what the user expects. If the user expects the application performance should be returned to them by tomorrow, then your simulation should be able to return it by tomorrow. That is what we need to model. Again, I purposely left out some stuff here. We will talk about it when we talk about what happened. Oops. There are other things that you actually need to look into. Say, for example, the level of SLA violation. How much this, when you run this violates, and how much this also violates. They also should correspond when you model. Here is an example of workload observations to create this. As I said, when we model, we need to look at the observations, and you can see that different classes of applications. Some of them are very trivial. You can classify that, and they quite often these trivial ones are very often like web services. They are the majority of the workload, and they use maximum 8 milliseconds of the CPU most of the time, sometimes lower, and input output is about 120 milliseconds. Light ones are 30, but most of the time maximum 20 milliseconds and so forth. Heavy ones will take about 900 milliseconds to 1,200 seconds. Now, it's only what I am actually telling you is the transaction classes, one application model. I have not added all that applications. Some scientific applications need in terms of hours, not seconds. Okay? So I just wanted to give you a background. When you model your applications, you get these informations. These are always available. If you go to many papers, you can get this information from there. All the papers in your area will give you this information. Okay? So really, the challenge is, the challenge that I'm trying to show you here is when you schedule these 8 applications that need 8 milliseconds, will not impact applications that are 900 milliseconds, right? So you can see that what what the challenges when you try to develop resource management and provisioning, the challenges you face. Some of them are very small, some of them have priorities because they pay more, some of them are sensitive, some of them very small in terms of CPU, but the disk, the reading they do is very heavy, and so forth. So that's why I added here. Okay, so most of the time people only look at the CPU, but applications also need other resources. Okay, so in fact, if you only look at this resource, there are some applications. If you see this one, for example, the first one, 40%, you can even assume that they don't even use CPU, right? In terms of proportion, they use more I/O. And if you simply ignore this, that is when you actually make a mistake in designing scheduling algorithms, because you only say this will take 8 seconds. And immediately after 8 seconds, what happened? You send another job, even though this is still there. So you overload the system. What happened when you overload the system? The system tries to consolidate, to do load balancing. And now it gets into another level of problem, which want to migrate. So if you don't take into account very seriously, you create cascading effect every time you touch anything. And I want you to pay attention about other resources as well. If you're modeling, see if the application actually does communication, I/O, and so forth.
Not all applications are having this much I/O.
No.
The portion of, let's say, the proportion of CPU and I/O,
yeah,
it varies.
Completely. It varies with applications. But what I'm trying to say is that there are applications do actually take other resources. Okay, some you can ignore. There are applications that actually use 2 hours of CPU, rarely read. See, the data is always in memory. They don't have to go to disk. But there are applications, in that case, the majority of time is CPU, right? So you can actually make some layaway with the amount of access to the memory. Sometimes if there is cache, this data can be fastly accessed from the cache memory. So you only need to take into account the amount of cache memory. Maybe sometimes when there is miss in the cache, they have to go and get the data from. That is actually sometimes negligible, because if it's doing 2 hours of CPU, it is CPU intensive job, you can actually assume that the I/O is negligible. But there are applications with the opposite. CPU is negligible, but lots of input-output, and a lot of people still only consider the CPU part of it. That's where what I'm saying, we need to actually, particularly when you do modeling, you need to actually model the application properly. Okay? So the reason I actually gave you this is it did happen to us. Exactly, it did happen to us when we were developing this simulation package. When we added consolidation, the whole thing started crashing, because it is just swap in and swap out, swap in and swap out, depending on the applications. So the system thinks it is overloaded, and the student was saying, "Sir, I only have two applications running on there." Finally, we knew that what happened. We then went and fixed that. So that is actually when the phenomena called thrashing can happen. Okay, so a task or a job, instead of executing, it spends only in being evicted from one machine, migrated to another machine, and come back to another machine. So it takes a lot of time doing nothing. We need to avoid that. Okay, so this basically put two resources requirements because I/O can have a great effect. There is another also memory you need to take into account, and there is arrival time, running time, total memory, I/O, communication, a number of virtual machines. These are the elements, the most features that you need to model. Okay. Now, each workload can be actually classified into two groups: workload intensity, which is arrival, and also number of how long the applications can queue. Some of the applications, when we actually run, some applications are patient. They can wait in the queue until they get assigned and executed. Some applications are impatient. Okay, so if you say, for example, you go to the bank, some people can wait until they get to the teller. Some people wait for 10 minutes and leave. So there are applications like that because if they stay there, the time for them to get executed, the quality of service time is very close to ending. They sometimes just evict. The system just says, I can't execute you. You get out of the queue. So how do we model that? It's a very interesting issue. Service demand is another requirement, as I said. Okay. Now, two probability distributions that you need. Okay, which we will do this afternoon. The exponential distribution. So some people actually use to model the service demand, this one, with exponential. I never use exponential distribution to do service demand, but I use it for inter-arrival. The job arrive one, and the second job arrives after the other one, to model the independent arrival. So there is dependent arrival where you have T1 will depend on T0, T2 will depend on T1. So that is dependent arrival. If you want to model independent arrival, you actually use exponential distributions. So it simply gives you the inter-arrival distribution of jobs into the system for you to model. So you can actually choose lambda, whatever you want, and for each x can be time, x can be whatever you want. You can use this exponential formula. Lambda can be as I did here, 0.512. You can change this, and you can see the results of changing the lambda, value, and then the exponential lambda, negative lambda multiplied by x will give you this one. So you can see this is when lambda is set to 2. You can see at some point at 3 it goes almost flat, and this is probability distributions of these job arrivals, inter-arrival, sorry. The other one is hyper-exponential distributions. This is what most of us use to model the service demand of a job. So it actually gives you a better representation of real life scenario because of that heavy tail distribution of jobs. Again, if you are not, how do I put it? You don't like maths, let me put it that way. Just let me know. I will sit down and explain to you with hands. Hyper-exponential distribution is nothing but this one, exponential. The only difference is oh, okay. Yeah, okay. You see, it is exactly this one, except we have two lambdas, right? For probability, you will choose this one. With this probability, you choose this one. Okay? And I1 to n, you can have many of these ones. That's what basically this says. You simply multiply for, if it is this one, P1, multiplied by lambda 1, this one, and that one. So these ones are the exponential, right? The exponential distribution just multiplied by the probability. Nothing else. Okay?
In earlier one it was minus lambda t. And now it is lambda
it should be minus lambda. Minus. This one is minus this one.
So finally that will convert into some kind of queuing. Some kind of queue will be generated on the basis of various stages we have shown in the.
This one?
Yes.
Some kind of?
Lambda 2 and you from lambda 1 somewhere else I am choosing
yeah.
some other state. So it will form a queue or some kind of queuing modeling will be there.
Queue.
Yes.
Not queue, it's how much time it needs. See, application wants to, if you want to model how much CPU time it needs, that's what I'm using this for. I don't use it for anything else. Some people simply use this. This doesn't give you the see, what this gives you is sometimes you get 0.1 CPU time, which is interreactive workload. Sometimes you get 20 hours, which is very large job. So it gives you a variety of, most of the time you get small service demand, and sometimes you get big ones, and sometimes you get medium ones, which reflects the real environment of execution of cloud computing. Most of it is web services with a smaller one. There are medium ones, and then some sporadically that come big one, very big one. That I'm just trying to model the service demand, how much each job wants.
So that will depend on the value of x.
Yeah.
How to decide probabilities? P.
Oh, you can set it 0.5. You can start it from 1. You can start it from 0.2. So you decide.
Set different values.
See what I did here. What I did here, I always do sampling. Here I used different values of lambda to sample what I get. And look at my workload modeling. I can then say this is the best value that I can use, and then I can use that one. So here you can also change the probability. It could be 0.1, 0.2, whatever you want.
And x is to be randomly generated between two range.
Yes, so it can be between 0 to 1.
Sir, that P is probability, right?
Probability.
Probability of what? Whether it is a completion time or whether it is a arrival time of
No,
each
probability of choosing which lambda. There is 1, 2, 3, 4. These are only two. I showed you two, right? Probability of using which way to go, which branch to go to.
Even the same thing is used in supply chain management also in selecting the part.
Yeah. It's used in many places, in many things also.
So what is the use of submission here?
Submission?
It is
Huh?
submission I.
Oh, well, you actually producing, sometimes, as I said, it will produce for you 0.11, and then it will produce another 0.12. So you actually use that one together.
Dependent.
I n equal to, so it will be some like P1, lambda 1,
E
To the
to
power
lambda 1
negative.
x P2 lambda 1.
Lambda 1,
lambda 1 and lambda 2.
yeah.
On same lambda.
This is same lambda here.
Yes.
This is same.
Plus
Or
all 2.
Yeah.
Lambda 1 plus all this one, lambda 2.
No. Lambda, this is together. Just look at this, like this
is
one.
only for those
पुराना
who
फार्मूला है वही लगा दिया तो प्रोबेबिलिटी को ऐड कर
if you are having n equal to 3, your lambda 1.
If you leave private,
लैम्डा की वैल्यू क्या रहेगी
if you leave priority out, this is exactly what it is in there, right? So I only multiplied it by priority. Nothing else I did because of the forking. That's all. I will come around and explain in detail if you guys need. We always do also what we call coefficient of variation. I will talk about this throughout. Now, when you actually do modeling and you do experimentation, you need to validate the result that you obtain. This is very, very important. Whenever you do simulation, there have to be some sort of validation. Okay, so we actually do this through a lot of statistical analysis. One of it is called coefficient of variation. Okay, the formula is very simple. BO is the standard deviation divided by the mean, and we will talk about this in detail also. Long-lived versus short-lived jobs. Again, this is another important area that we need to look into. They are what I mean by long-lived processes are long-lived tasks that actually have maybe small CPU but long waiting for data to come over the network. The network is slow or long-lived because they demand CPU more or whatever. Now, what this formula says is that you have a period of time. T is capital T is a period of time. Sure. Stop.
जो दूसरी वस्तु ये वो सारी चीज़ें बता दें, इसका हम ध्यान देंगे। ये सारे ट्रांजेक्शन्स में भी बता देंगे, इसलिए और उन सब चीज़ों का ध्यान रखते हैं।
So basically, if you divide this peak time into what we call epoch, so time equal or as much as you want, you divide them, and we say that this is in plain English. Basically says most processes are short, but a small number are very long. This basically what this all says, which is true. If you look at any trace for any system, you will see that most of the jobs are small. I'm not going to touch it myself. Huh? Ah, you have mouse in my pocket. Now I know.
इसी वजह से हो रहा है।
Okay, so this is basically what we have modeled so far.
This alpha is what, sir? Alpha stands for?
This one
Alpha is actually representing what?
representing the execution time. Yeah. Okay. Remember here in this diagram, this consolidation. I know some people are sleeping. Morning. We'll take a break. I think I promised an hour, but it's almost 2 hours now. We have still 13 minutes left for lunch. I will just take 13 minutes. Remember, I don't mean in a negative way. I don't want to overload you. I already told Professor Dykes that we'll do it 1 hour, 1 hour. But I forgot and kept going. So, but I told you, right? I'll do 1 hour. But I forgot about it. Sorry. Remember, I told you consolidation. Really, if you look at it in the 90s, we call it load balancing. Now it's called consolidation for 2 reasons. One, to really more migrate virtual machines to save energy, or to distribute the workload from heavy loaded or from underloaded to appropriate or lightly loaded systems. Okay, so mostly we do it nowadays really for energy purposes. Okay, so when you do cloud computing schedule running, you need this. It has to be there. Okay, because of dynamic environment you are modeling, you need that. So selecting virtual machine for migration is a very big problem. It's a PhD problem. Virtual machine running on an overloaded machine, physical machine, will receive a very bad service. Okay, and similarly, the underloaded machine will consume a lot of energy and sit idle, doing less work. So we need to actually balance the load by now moving some of, if we have some systems are overloaded, some are underloaded, we want to move some of these virtual machines from one to another load. Now we have 3 problems here, which I will formulate tomorrow, all of them for you in a mathematical formula. 1, which one you select? You have 4 processes I think I have example here. Yeah. So we have some processes. One of the issues is which one of these, this is on one node, one physical node, which one of these processes should migrate from this overloaded node? The second problem is to which node if you have multiple nodes. Now, mind you, because of the dynamic system that I am actually modeling, the node I am saying now is underloaded can all of a sudden become overloaded, right? And then you move a job there, what happens? It says, oh, I'm overloaded. And now you move with job again, you get into this. This is why I say it's a serious problem that we need to actually, a PhD level problem. So, that's one problem. Which node to move to is another problem. Load balancing, okay. It would be most beneficial if we could identify which virtual machine that may be expected to continue to run, which one will run, which one will move, and select them for migration. But how can we know in advance whether virtual machine is going to finish executing soon or not? The other thing is that I have 3 processes. One is almost about to finish. One is in the middle, and one is really just started. So if you move the one about to finish, because migrating actually, it takes a lot of time, right? So while it's migrating, the job is just wasting time. It's not doing anything. So it is response time increases. Now, if you if you select that one, you basically did something wrong because it's not beneficial, right? So that is the third problem you need to solve. Here is the example. As I said, we have V1, V2, V3. V1 consumed from where it started. V1 started at 0. All of them start 0. It has done 16. No, it has done 12. Yeah. Its remaining time is 4, right? V2 still has 44 time unit. V3 has 10 time unit. If I select this one, now the reason I put here, we have tried this. We have said the job that actually took long, already served long, it's about to finish. But I will show you this is not true actually. You can predict actually a job that has taken T amount of time will still take another T amount of time. You can predict this from what it has done. Okay? But I have seen people simply saying, oh, this job has done 20 minutes. It's probably about to finish. I won't touch it. This is the example here. It has run 20 minutes, and you can say, oh, this one I don't touch it because it is about to finish. So you can assume that this is about to maybe 1 second left for it. I will leave this. I will actually either this or this one. You move. So if you move, and particularly within cloud environment, if you're moving from one data center to another data center, then this 4 time unit can become 200 time unit. So you increase the time unit. Migration is very, very tough problem that we need to take into account when people simply now a rush of papers that they consolidate the system. When you read the paper carefully, they actually made the system worse. Why? Because they did not actually look at these things. You can see the algorithm. They did consolidation. They actually managed brought down the power usage, energy usage. But if you know the area and you look at it carefully, they actually increase the usage because they did not take into account what I gave you this scenario. If you just submit this scenario to their systems, you will see that some of the jobs simply what's called trashing, going in and out of systems and going in circle. Okay, particularly when you try to minimize energy, you need to have, or you need to actually connect all of these jobs into smaller physical machines, and you switch the other ones. Or you can actually lower the speed of the CPU to save energy, which means you can actually now slow down these running processes. Okay, it's actually better, rather than migrating, better to slow down, because sometimes if you make the wrong migration, you actually worsen the violation of service level agreement, you worsen the consumption of energy. So, again,
so that means there are two objectives
Yeah.
while making migration.
Yeah.
One is the timing and another is the energy consolidation.
Yeah.
So these two objectives should be looked into together while making migration.
Absolutely together. The time, the type of the process or the task to be moved has to be looked also in as well. Yeah. So it is some sort of multi-objective formulation for
How it would be
this.
easy to have this lower down of speed in multi-core systems?
Load balancing?
Lower down the speed of CPU in multi-core systems.
Down?
He is actually talking about frequency scaling.
Yeah.
Reduce mic, no, not audible.
No, actually, my question is they're related to change of frequency.
Yes.
Or the speed, lowering down the speed of CPU.
Yeah,
In
scaling
case
down
of-
or scaling up?
Yeah, in case of multi-core system, it is viable to do it in the same manner that we can used to do in a single core system.
Why not?
Because I mean, every core we have differentiation of the work being allocated.
Yeah.
So wouldn't it affect if we do it on one machine or on different cores of the machine?
No. In the multi-core system, you have basically one box, and then you have multiple CPUs in there.
Right.
So yes, you can actually lower the CPU, the voltage, or scale up the voltage as you want.
Particular CPU.
Yeah, one CPU.
Okay.
Yeah, you can do that. It provided that the system actually allows you to do that. Okay. Now, as I said, the overhead is a very serious problem to look into when migrating virtual machines, and the ones that actually finish soon. If you migrate them, the overhead will basically kill you and waste a lot of time and waste a lot of energy. And this is where we actually can observe some of the SLA violation, and also the virtual machine cannot run during this time, so you increase the response time of this particular application or task, and it is very important to simply take into account these issues. I will talk, if you give me just 1 minute, it's 12 o'clock. I will talk about this in detail, but now I will just give you some of, these are what we use to measure the performance of our system. Okay, so some of them are standard. The response time is very important for interactive workloads, particularly web service applications. If you're actually running web service application, you use response time. Okay, so for the applications like throughput applications, I told you, response time doesn't make sense. So you make sure that when you write papers, you know exactly which of these metrics you use. For interactive applications, as I say, always response time is the best performance metrics. Throughput is for the throughput, high throughput applications that I told you when I talked about the bag of tasks. This is when you actually use throughput performance metrics. Scalability is usable for any environment. So what basically scalability says is that I am running or I'm testing my resource provisioning with 20 tasks. Should I actually increase this by tenfold, the performance should also increase proportionally, right? It should not actually exponentially increase. So it should scale appropriately. That's what we're saying. Scalability of the system, you can run the system, you can test the system with small, and it should also give you the appropriate scale with if you use more. So that's basically what scalability says. It's not nothing. Just you can use it in any environment. Now, cost, energy. These are what I'm just telling you is this what we call mono performance metrics. When we formulate, we can formulate one or two of them. One is simply response time. But if you actually say, for example, scalability and cost and energy together, you can actually look at them together. So these are multi-criteria. It's not one, but two objectives, multi-objectives, where if you look at response time, it's only single objectives. Very easy to formulate, very easy to show that is correct. Cost is actually how much cost you pay for your application. You, as a user, you want to minimize this cost. Energy is the cost of energy. Efficiency is, again, here, this word is used in a very loose ways, right? Efficiency means many things to many people. So you need to properly define when we talk about efficiency. I put all of this because I collected them from literatures. Efficiency, sometimes when I review, I get a conflicting definition of efficiency. I want to see a clear definition, what they mean by efficiency, and then how they prove that this is efficient. You can't just make a claim, you want to also support your claim. So that's why I put up these things. Elasticity, because the cloud says elasticity and scalability are cousins, okay? So elasticity, it can go up and it can go down. The system can scale up, can scale down. These ones, just availability is system available 99% of the time or 99% of the time. Reliability is another issue, okay? Reliability can refer how reliable the system is, including security. I put security behind reliability because we can actually talk about security when we talk about reliability. Is the system reliable from security perspective? When I say the system is secure, I'm saying the system is reliable. When I look about fault tolerance, I can say the system is reliable to fault tolerance. So reliable, also it is important when we talk about reliability, we need to actually make clear, here I am talking about security or I'm talking about the fault tolerance of the system. Security, as I said, is nowadays is very hot area, and this we have been doing this resource management and resource provisioning, security aware resource provisioning. but it's not that much. It's a lot of scope for PhD thesis as well. Now, I showed you in this diagram, this is SLA negotiation, right? So this SLA, once you negotiate, it becomes a document. And you need to observe that as service provider. If you violate, you actually have to compensate the user. And it also, the degree of violation determines the compensation. Now, many papers don't actually connect this. I want to actually see what level of degree, how can we model real life situation by saying, okay, here is the level of violation, and the compensation also should be commensurate with the level of violation. Okay? Now, this performance matrix or criteria can be divided into two. Okay, so we have to do this always. One is what we call user-oriented or centric performance, and then system-oriented performance. When I talk about system, I'm actually interested in maximizing the utilization of the system, because that is improving the cost, right? As a service provider, if my system is utilized more, that means more money for me. So I'm talking about now from from service provider or systems perspective. For the user, the cost means I want to reduce my cost. Now these two conflict. So that's when we try to balance. And you can see that response time is also system-oriented performance metrics. Energy, again, system-centric performance metric. Okay, so we always look at them in two ways. One is for the system itself. So if I am trying to improve the energy consumption of the storage, I'm looking at the system perspective. Okay, it's not actually the user perspective. User is interested that his data is safe and stored and accessible at any time. But the owner will actually make sure that this, whatever user wants, okay, but I want also to make sure that this data is safe and also doesn't consume a lot of energy. So how do I actually do that? So what I'm trying to tell you is that these two, the user and the service provider, are always in conflict, but they can't live without each other. The idea is to maximize or minimize these ones. Some you have to minimize. Now utilization you have to maximize. Okay, cost from user's perspective you have to minimize. From service provider's perspective you have to maximize. Okay? All right. We can have a break and come back. So we'll talk about it then.
Is there anyone who hasn't signed the attendance sheet? Is there anyone who hasn't signed the attendance sheet?
Okay, let me continue.
Now, because you have a lot of questions, I will just do one or two slides and then we can talk. we want to actually now look at energy consumption, which is part of that. Here we have the applications, and we extract some features from these applications. One person was just asking me about this. I don't know who was it. He's gone, I think. He just asked me about this. Now, tomorrow I will talk about this in detail about this. We extract some features from it, and we use this feature and do feature selection. Based on that feature selection, we select a subset of features and do regression analysis on these features. And then we evaluate the regression using regression method and produce results. Basically, we want to model energy consumption using regression analysis and feature extraction. So it is okay to do for one. As I said, if you're doing it for all types of dynamic features, is very, very difficult. So not only we model, we also we also use this to test energy conservation of data centers based on this model. Now, I will actually talk about some of these quickly. Now, MakeSpan is a traditional, very well used performance metrics. Okay, a job slowdown is another performance metric that we use. In particular, remember I gave you an example of a big job being scheduled before the small jobs, and the small jobs get slowed down. So these are the kind of things you can do. But these two deal with these two metrics: workload speed up, this one, and workload slow down, this one. Now, workload speed up is basically MakeSpan of the workload, and you find the summation of the workload, and this is the response time of each workload. So you can actually get the workload speed up by using this formula. The same for workload slow down with this infinity here. It takes the workload, you first calculate the MakeSpan of the workload, and you actually select the maximum of the workload response time and divide by that. That will give you the slowdown of the workload. Cost metrics. There is actual cost and there is charged cost. The actual is basically depends on the virtual machine, actually, the size of the virtual machine and how many you use them. So if you're using 4 of them, for example, you need to actually sum up. This is the start time of the virtual machine you used, and this is the end time. So you get the time for each one of them, and then you sum up. That gives you the actual cost of the workload time. The charged cost is actually the upper limit of really basically this one. Time stopped, finished, take away time start, and how many virtual machines you used if you add them up, but take the upper this, and then that's what you get charged. In other words, usually we round up. If it is $22.90, we make it $23. Okay, so these are the cost metrics, but again, I am just giving you the easiest one. I will talk about there are many different costs that are used. We will talk about them. Now, there are also compound metrics. Cost efficiency. Again, the one I actually like is the utility, because utility gives you an opportunity to include negotiation. So when you have service level agreement that you negotiate, then utility becomes very important to include in there. That is what we try to capture here. Unfortunately, I put this together and I can't see it. Yeah, but I can't see it. Anyway, I want to capture this. The most important thing about this utility part, which I'll talk about this utility later when we talk about SLA negotiation in particular, is how to decide utility. And again, somebody has actually asked me about this. I, as a user, want to optimize my utility, and the other negotiator is also wants to optimize the utility. So the service provider wants to optimize their own utility. I, as a user, will optimize my own utility. Then we negotiate, and we need to include into this, which is not actually here now because I didn't want to make it more complicated. Cost efficiency is you take the cost of the workload, actual cost, the real cost, the cost that you charged by the cost that is actual cost. So that is what the efficiency is. Okay. Basically, what we did today is we looked at the workload characterization. What is it? What is it not? And basic concepts, workload descriptions, and modeling. Also, we looked at representatives of workload models and talked about methodology, which is basically the introductory level. We will get into detailed one. Choice of an analysis standpoint, identification of basic components, choice of characterizing parameters, and in terms of traces, what data you need to collect. But if you actually have, from cloud point perspective, if you have workload that really needs real time, it's better to do it what yesterday we called fog computing, because it is the latency sensitive workloads don't actually say I'm using clouds, because the time they need to go from point A to cloud and the latency is makes them useless. So these are the kind of applications that are not really very good for cloud computing. Very, very latency sensitive, are not good for cloud computing. Anyway, I will stop here. If you have any questions, I'll be happy to answer.
So can you actually explain the idea of energy consumption that you have shown with that graph?
I actually have one lecture on energy completely from A to Z. Okay, so I'll just give you the background. We are just modeling energy consumption for cloud data center. What we are saying is that if we take applications, we can extract some features of these applications and then use feature selection algorithms. Okay, and then select which of these features are representative. If you remember earlier, I said I wanted to do it for all dynamic jobs. I could not do it, I stopped it, but this is not for dynamic environment. So the workload, this is basically we used workflow application, which we pretty much know it is structure and its features, but we still put it through some feature selection algorithm, and we used a subset of those features to feed the regression model. And through regression model, we can actually now evaluate our model. So you give me a data center, and you give me these workflow applications. We will actually tell you this is the energy consumption for this set of applications from time t0 to time tn. So we are just modeling, okay? But there are a number of papers actually. I think we first came up with an energy consumption with resource provisioning model. I think me and Rajan, our PhD student who is now working for, I think, Google in US, we actually came up with that idea. I will talk about that idea also, and I'll give you, I think I have that paper here. This one. Okay? But this is only one of them. There are a lot.
Sir, I am a little bit confused between resource provisioning and resource allocation.
Okay. Oh, you mean the definitions?
Difference between resource allocation and resource provisioning.
Okay. What do you think? What's the difference? Just tell me your idea.
I think resource demand, actual resource demand of any workload, and what is given to the workload, resources to the workload. Actual.
You provision, you provide these resources.
Yeah.
You provide.
Okay.
But the allocation is different. You map it to a physical location, okay, to a physical processor.
Okay.
So we have physical machine, right?
Yeah.
And we say here is, we will provide you with these resources, okay? But you may only need 2 of these resources instead of 10 resources that we provided you. You can allocate all your resources, all your applications to 2 of them. So allocation is mapping,
okay,
logical to virtual machine to physical machine.
Okay.
Provisioning is provide you with virtual machines. You requested large virtual machine, medium, whatever, we provide you with virtual machines.
Maybe I can also ask.
Yeah.
Sir, it is regarding one of the very first few slides in which you talked about server consolidation.
Yeah.
You can come on.
Yes.
Yeah, this one. Sir, here you say for the workload generation, we talk about workload description. It may include QoS. But what I feel is, once the workload is there, when we talk about scheduling, we try to optimize the QoS parameters. Let's say, if we talk about, let's say, optimization or minimization of the turner. But how can we include QoS in the workload description itself?
That's a good question. You see, QoS can be included in here. What some people will do is, remember I gave you a simple example. I want this application to run and response comes in tomorrow morning, but I'm going to pay in Indian rupees. I don't care if it runs in America or in China or in India, but I will pay in Indian rupees. Okay, now that is actually part of quality of service, right? When you say the time is exactly tomorrow morning or before noon, I want to get it back. So this is quality of service in there. Another way is you leave out quality of service in here, but you negotiate. You say, I actually need this job to be returned tomorrow. So here, actually, I could actually add another arrow from here to workload submission. If the workload submission is a broker on my side, that can actually, most of the people actually do that. The broker is the one that negotiates with service providers and give you a set of responses, suggestions. This is what this service provider says. This is what this service provider says. I recommend this service provider. This is what we can have here. But to simplify, you can add quality of service in there as long as it's not a complicated one. A simple one like the one I said, I want this job returned by tomorrow. So I know exactly this is a simple one. Response time is 2 o'clock on September 27th. So when this is submitted, if I submit it now, so I know the end, right? The start time, the submission time, or the arrival time to the system, which we call submission time. My end time is my quality of service. But if you have multiple requirements of quality of service, I suggest to actually negotiate with service provider. If it is a simple one, like the one I'm using here, you don't really need to negotiate, because unless it is real-time job that you want to submit now and you want to get the answer in an hour or so. Like my laptop is dead. I want it yesterday before today, but I can't do it. So I'm happy to wait until the service provider says I can fix it. Right? In that case, right now, all I have to do is until he calls me back and say I can do this. We now negotiating. I much prefer if resource management component can actually negotiate with brokers. Brokers are agents on behalf of service provider. Or on behalf of user. So if any one of your new students want to work, they can develop a recommendation system in here that actually finds out the appropriate quality of service and give it to the user and say, I recommend this for you. Many users actually don't do it. I only put the quality of service in here to show you that most people simply know that I want it back tomorrow. I want it back today. I want to pay it in Indian rupees or American dollars or something. Quality of service so far is very simple. But there is a scope of recommendation system here. Again, now in this, when you get into this recommendation system, trust management comes into picture also. Who do you trust? Okay, service providers can say I will do, or if you have some recommendations sitting there, which one is truthful, and how you collect that data. That's why I say it's a PhD level. Again, a very good problems to work on.
Even sometimes it can be even repetition based.
Yep, yeah, reputation based as well. Yep, yep. Any other questions? I'm happy to answer. Anything? Yes.
Sir, we are using regression technique, which is a type of supervised learning. So, how this will be helpful in making the deployment self-deployment? Will it be achieving a self-deployment type of thing? Something else?
Self-deployment? On where? On the cloud?
On the cloud.
Which side? User side or?
It can be any type, either user or from the host.
No. You
I'm
can't.
not understanding why we are using regression here. To make it
Regulation.
regression.
Oh, this one. You're talking about this one. Is it this one?
Yes, sir.
No. This one, I was actually modeling energy consumption. It's not deployment here. How much energy the system consumes given this application and this data center. It's not deployment. See, one of the things is energy to optimize, right? So before you optimize, you want to model how much you expect to consume. If you know how much you consume or predict how much you consume, you can minimize it, right? That is what we are trying to do. To minimize here, one way is to do it dynamically while the system is executing by moving around virtual machines. Remember I said sometimes you get into thrashing, very similar to memory and cache, memory thrashing, very similar to that. So to avoid that, what we want to do is we want to predict what will be my usage, my consumption of energy. If we can predict that, we can now say, okay, here is what the workload will be using. Then we can shut off 4 or 5 machines and schedule the rest of the tasks on 3 of the physical machines. That's all we do. We are not scheduling you said self-mapping? Self-deployment. We are not doing that. You can actually use this system, okay? You can change this. You can do many things here, right? There is support vector machine. There is, you can do many all of these things. What you can do is for self-deployment. Last year, when I gave a keynote here, I actually talked energy as one of the main sources. So if your application costs, if application consumes more energy, we will charge you for the energy you use. So if you don't actually optimize your application, then I'm going to make you optimize it or I'm going to charge you. So self-deployment can employ this, right? I'm trying to self-deploy to minimize the cost. I will see how much energy my application will take by modeling it. And then self-deploy and run the application. You can actually couple it with this very nicely. Other questions? Anyone?
For data intensive applications. I read many papers, but I could not find that how they are modeling data intensive application, because in data intensive application the difference from normal applications that there are 2 types of nodes. data nodes and compute nodes. Identifying how they are generating the graph for application.
The graph, you mean I/O intensive applications?
No, data intensive application, intensive application, same like big data application.
Yeah.
Yeah, there are two types of nodes here. Data nodes and compute nodes. And there are communication between data and compute, but there is no communication between data. But
there are many papers in that. Too many actually. If you specifically, if you look into grid area, so there is data grid and computational grid. The data grid is actually where you find this kind of papers. The data grids are what you just said, data storage, and then you have compute nodes in there. I have this. I will show you. I think we have many papers in that area. I don't remember, but you can look up other places as well. See, this is what his question is. In fact, we published a paper in this area. You see, this is compute node, and this is storage node. So the data can be read. Some of the times you can actually duplicate the data, but you need to be careful when you duplicate the data, particularly if it is changeable. You know, you update the data, you can have multiple wrong updates. You need synchronizations. So this is a scientist working here on this data, but this scientist, she needs also to store the data and to compute and also store the data somewhere else, the result. So we did this is there a lot of, but this is for grid computing most of the time. There are one of the most important questions he raised is many papers are written for CPU. You know, they always work in CPU response service demand. So you need to couple. There are a lot of papers that do couple multiple criteria. So we call them multi-objective algorithms or resource management. It could be energy and or it could be data and CPU. Sometimes you have to do CPU communication and data. Particular, again, it depends, okay, on type of scheduling or on type of the applications. Tightly coupled applications require what is called gang scheduling. So if you do gang scheduling, then you really need to worry about all those things. For bag of tasks, they can run anywhere, right? So they can run here, here, here. If they are tight, they only run in certain areas. Otherwise, they are useless. Gang scheduling becomes useless if you distribute it to many places. So this application is actually a bag of tasks. Most of these scientific applications that we run. So it is there. You just need to focus some of the, when you do the Google search or whatever, they are there in the area of data grids. Other questions? How many of you used cloud computing? Real cloud computing. Is there anyone who haven't used cloud computing yet? No one used cloud computing yet? Huh? Huh? Yeah, Gmail. So you've used, everybody's using, right? So everybody's using cloud. Now Twitter is building another big data center. They already bought the spot and everything. So the amount of data they're generating, they couldn't keep up with, and they keep building these big data centers, and a lot of scope for research in resource provisioning, particularly with adding big data on top of it. Big data analytics will consume a lot of CPUs, storage, energy, everything you touch in there. And Internet of Things will even complicate the scheduling further. And with smart meters, smart cars, smart cities, the scope is the sky is the limit. So there is a lot of work, very nice work coming up with in terms of resource provisioning area. Okay?
The biggest problem is data veracity.
Yeah, data veracity is the problem. Yes.
Like a huge amount of data is being generated, but how to store each and every data is not feasible also. So how to decide that which data is to be discarded and which is to be retained?
A serious problem.
It's a very serious problem.
Yeah. So what we call now is data hoarding. If you collect all the data, you hoarding, and you keep buying storage time or storage. The good thing is storage systems are actually, the price is going down every day. It's going and going. And most of us, the more it is cheaper, the more we want to buy. That's another economic problem, right? Because we get enticed. Cheap, let me keep this data, but most of it you don't need. Data has value, right? And this value can decay depending on the type of value. Sometimes, if your taxation officer can tell you keep your data for 7 years, you have to keep. But some data that doesn't have value, you need to delete. So the problem is how to determine the value of the data, and also along the timeline, right? Data can be valued for 3-4 years, but after that it has no value. How can you determine that? That's a big research problem.
Why do you say only 3-4 years? Do you need data which will be required?
What is it?
Why to retain it for 3-4 years? Why is not lifelong?
Yeah.
Maybe somebody's health history or
Yeah, but you see, as I said, taxation office will say by law, you keep your tax return for 7 years. They can come back to you anytime during this time. You have no option unless if you destroy, they come back to you. They will say to you, you pay more, you pay. There are some data that some companies, auditors will come once a year, audit, and then after that, this data has no value. Once they say it's okay, everything okay, sign, you can delete it. You can keep some data depending on the applications. If a person dies, why you keep that data? Because you want to do research on it to see why from that person who died's perspective, that data is useless. But from research perspective, it's good because you can actually do some analysis, data analysis on it to find medication, or to see how long this person lived with cancer before she or he passed away, and what medication was kept this person longer, or how worked, or for whatever. So data, medical application can be useful anytime actually for a long time. So it depends on what is the data used for. The value, when I talk about the value, that's what I mean. The value of the data determines. Stock value, stock data has value of the shortest life, right? If the stock price of your stock change today, then in the next one minute, if you don't sell it, it has no value. That data is already out, right? The stock says the stock value is $10 now. In 2 minutes, if you think it's going down, you sell. If it's going up, you buy more. But this data has no value anymore because you know the price. Everybody knows the price. It has value before it is disclosed. Because if you know before it's disclosed, if it's going up, like you know this digital currency, right? Bitcoin, cryptocurrency. It went like hell to $40,000-$50,000, just starting very low, and now it goes down from there to 9,000. So if you have the information inside information earlier, when it hits 40 before it goes down, you can sell it. You can be a millionaire. But if you didn't know, it went down to 9,000 from 40,000. You lost big loss. So the value of the data is only useful before it is disclosed. So application decides which the value of the data, or the data itself decides the value with some by legislative requirements. Any other question? Okay. See you later. Show you a model, a really compact model that allows you to generate a trace of syntactic workload. So here is a sample of workload. So this is actually matrix multiplication. So what we have is the main task here will split the data by row and column and give it to this one. And then this one will also take, so you have the arrow there. You see, this is how many numbers of tasks you want to create, depending if you want to give 2 rows, 2 columns to one, or 1 row, 1 column to a task. Depending on task, on that, you create this width, okay? And then when they finish, they will all send the result to this task. Then this task will combine them and produce the final result. So this is called matrix multiplication. Okay, it's very, very simple one. But this one is multiple of that. Okay, but it is more than that. There are applications that have this structure. So when this returns the result, then this will split the result produced by this and this, split it, and then pass it on to these ones. Then these ones will compute, and then send it to this guy. This task will also now split the result. This process continues until the last one gets it, and this combines the result and gives it to you. Okay, there are many applications in science that have this structure. And this is another structure. Okay, the maximum width is from here to here. This is actually sorting. It does things like this, shovel sorting. You can see the structure of this application. The main task will actually distribute. I get USB now. I can give it to him. You can get the slide right now. He will do it for you. So I only show you applications, but you can actually model many applications more than this. And okay, so this we simply call it, you see here, you fork, and then here, this it joins. This only has one phase of fork and join. So if you look at this one, what do you guys think from yesterday's class? Anyone remember yesterday's class? Do you remember map and reduce?
Yes.
That's what it does, right? So it simply maps and reduces, map and reduce. Okay. Now this is, before I show you the model, this is what we need actually, because if you see these ones, if they run on different processors, they need to communicate, right? So when this one splits the data, the matrix, it has to send one to this one and the other to that one, right? So there is communication involved. Is that okay? Okay. So you need to actually model communication like this between these different processes. So T0 is the startup time when the communication starts. N is the number of nodes involved. In this case, if we have, what do we have here? N. So this is the N, okay? So that is actually the N. You can see this is the number of number of nodes involved in the communication. And R is the asymptotic bandwidth. This is basically defined the maximum bandwidth achievable when the massive legacies approach infinity. So many communication, LAN or WAN, they will give you this value. Okay, this is the maximum value. And sometimes you get also maximum processor value. But this is benchmarked on some data that the vendors do usually. So you can also, there are many research people also do this and then find out the exact value of R. And you can find this many places. And M denotes the number of bytes of data to be transmitted. So the size of the data that you need to transmit from point A to point B, from one task to another task. So if you have these values, then you can actually use this to model the communication cost. Okay, every time node A sends data to node B, you can actually use this to model the communication cost. Okay? Okay. This is the model that allows you to create any one of these. Okay? Basically, this is actually developed by Savage, who passed away a couple of years back. Just as I finished my PhD, he passed away. But I used a lot this workload model, very good. But basically what it says is that if you have a set of processes, a set of virtual machines, P in cloud computing is the number of virtual machines. But in this case, is the number of processes. The number of processors allocated to the job, which is exactly what virtual machines is allocated to you. Okay? So given a set of virtual machines, the runtime of your application, this is what Savage execution time function says. The runtime of your application is equal to the load. This is the load imbalance in the computation represents, and this is represents the division This is the amount of work that your application will do if it is divisible by the number of virtual machines. So if you have an application that takes 20 minutes and then you have two processes or two virtual machines, each one of them will take 10. So overall, because they are processing in parallel, the execution time will be 10. That's what this says. I think I confused you, right? No, it's okay. Okay. So you need to multiply this by some imbalances. This is a weighting factor because we don't know, right? Sometimes due to sharing, due to networks, something will happen. That is why we multiply this by that value. And the amount of sequential computing, so there is parallel, right? The tasks will compute in parallel. But they are in addition. You see, this is, I said 20 by 2 is 10. That's the ideal, right? But they are overheads. Communication overheads, internal overheads, because CPUs sometimes, operating systems do some things. That this part actually models that. The additional time that it takes. And B represents amount of communication and congestion overhead that increases with the number of processors. So what basically this captures is that the more processor, the more virtual machines you have, the more communications it occurs, the more overheads you incur. That's basically what it says. So sometimes you want to minimize the number of virtual machines given to you because you can minimize the communication between them. Okay? So that's basically what this captures. I have already talked about this part. So
this is the total time taken.
This is the total time taken. The total time that your application will execute. So it includes then how much time each job or tasks will take, plus the overhead. So if you see intuitively, it really captures the whole thing very nicely.
Why this phi is included?
Where here?
Yeah.
This is a weight because basically what we're saying is that there is sometimes the processor may actually have local jobs running on it. So then if we have two processors, right? Now one can little bit slow, right? Maybe some jobs locally running, and so there is imbalance between them, which means one can take 10 because there is no other interference. This can take a little bit longer, so the overall time can be not 10. It could be 11 plus overheads. It could be 10.2 plus the overheads, this part.
So the unit of alpha is also time.
Time, yes.
Unit.
Yes.
Of alpha.
Yeah. Now, this basically, this P, you see number of virtual machines. This is how we actually compute the number of virtual machines assigned to you. Okay? Basically, if you have this 0, there is no communication, right? So this models bag of tasks. There is no communication between them. Then you all simply have run. Then this becomes simply no cost. But if there is communication, then you really need to calculate the maximum the maximum number of the optimal number of virtual machines that you need. So this basically, you can see here, we use the number of processors. We assuming here, in real life, if you have multiple jobs that have multiple tasks, they always happen to be in squares. They need 4, 2, 8, 16. They actually always, this is proven, that is the way the tasks are actually require processor. This is basically what we say, is square of processors depending on your workload. And you can also execute this to get these two values, okay? Here. Now, this is actually the table for all the values that you need in there that I used for each one of these. So, the number of processors, I better look at, because I can't see there. There are 64 processors. We choose 64 virtual machines, okay? For TP, we used that formula I just showed you. That is how the execution time of each workload is modeled. And you remember the hyper-exponential? That is exactly this one. Okay? The one we did in the morning, that's exactly this. The service for this. The coefficient of variance that I talked earlier, I set it to 1 to 10, and this is actually expectation of workload. So this is set by 16.36. The maximum parallelism, the system has 64, but the maximum parallelism, the maximum number of virtual machines that I assign to my job, is uniformly distributed between 0 and between 1 and 64. So 1, because the job is sequential, it only needs one machine. But maximum is the entire number of machines I have. Okay? Okay, so this one I already showed you how we model this and this one, these two parameters. These are 4 different workloads. By using this algorithm, you can just change the values and produce a number of different workloads. So I call here workload 1, workload 2, workload 3, workload 4. The 3 workloads I showed you earlier, they are actually these workloads, these 3 workloads. I just didn't put workload 4 in there. So if you see, all I did is actually I'm changing the expectation for each one of them, and this is actually the utilization. So if you look at workload 1, the execution time on one machine is 14.06, and the execution time with alpha is 0. But here you can see that this is infinity. What this basically says is that these tasks don't communicate. They are independent. The matrix multiplication one, that's what I'm trying to model here. The second one, I put mu to 0.4. There is communication between them. Okay, the one you remember that has fork, join, that one. And so it goes like this. If you continue doing this, now these are actually the execution time on one machine. And this is the execution time on one machine for workload 2. This is execution time for workload 3. Okay? And the inter-arrival time, you remember I told you the exponential distribution. So the arrival time is Poisson, but the inter-arrival time is the exponential distribution. This is how I generate, actually generate about 10,000 jobs, and then these 10,000 jobs will run on 64 processors, and this tells me how they are inter-arrive after one another. So this is the mean. 1 over lambda is the mean, and this is how I actually calculate that. I better look at here. I can't see there. You don't see it there, do you? You can see it?
Yes.
Okay, I can't see it. This one is the communication, right? I already showed you how we compute the communication. And the mean is basically for each workload, how much it takes on one processor divided by the total processors assigned to this particular job and multiply by the load. And the load is the overall workload. Okay, so this is how you actually get the mean of the for the exponential time. Now overhead. So basically, what I do is that I assume that there are some overheads that we can't account for, but you can change this. You can try any number. What I'm doing here is that 1% of the execution time. So if the execution time is 20 seconds, 1% of the execution time will be added as the overhead. So I'm accounting something happened, trying to do the worst case scenario. Transfer for
transfer factor.
Preemption overhead. So what happened is that because this, remember, we are talking about virtual machines that share physical machines. So this, when they share, they actually, one gets out of the processor, the other one goes in, gets some service, come back. So they share time sharing. So that is what the preemption overhead is. Every time a virtual machine leaves for another virtual machine, then we say that time is about 10 microsecond or something like this, okay? So we are counting overhead in there. So as you see, there are 10,000 jobs, and it takes about a couple hours to run them. The reason I use 10,000 jobs and 10,000 times run, usually I throw out about 500 to 5%, whatever you want, as a warming of the system, because these are statistical executions. What I do is I call it warm up. So I threw this the first 400, 500, as much as you want, okay? And then you take the rest and you average them, you get a very good outcome, okay? So you run this multiple times, of course, you don't run just one time. The transfer factor and the branching factor, these two are because I'm using what is called hierarchical scheduler. So this hierarchical scheduler is sort of a tree. the branching factor is the number of children of a particular node. So a parent has 2, and this becomes branching factor of 2. MPLD is multi-programming level, so which basically says we can actually restrict the number of virtual machines that can run on a given machine. So we can say 2 maximum, we can say 4, but you need to be mindful, right? When you schedule, if your system is powerful, 4 virtual machines can share your system. But what we call context switch, right? When one process goes, one virtual machine goes out and the other virtual machine comes in, there is a context switch cost, which is overhead. Somewhere I said that, I can't remember. Huh?
10.9.
Yes, so that one is actually the cost. So you buy, if you have 4, you multiply this by 4, this overhead continues and it increases. Now, this model is very good model. And today I want you to model this. Now, it looks horribly difficult. It is really not. Okay? So, what you really need to do first is do the inter-arrival time. So, yesterday we created what? Job arrival times, right? Dependent job arrival time. But now we wanted to make it independent job arrival time. So there is inter-arrival time. We can capture this by exponential distributions, which is basically this one. Okay? Now, for you, you just need to set lambda to 0.5. Don't do anything. Lambda is equal to 0.5. And you have almost the answer, right? You just need to produce t, right? For t, or every time inter-arrival to generate t, you just use exponential distribution. The value will become for the next job to arrive. Then again you run and it will come another value, and then you have a very nice inter-arrival time of the job. Okay? So when we finish that, we want to do service demand. The service demand, we will use the hyper exponential, this one. Okay? So how do we start? I can walk around and help you with. We need to start with exponential distribution. Okay? First, do you have any questions? Any questions about this model? Where did you go for the slides? Oh, Luna, come and take now. Hmm? Where is the slide, PPT? Just make it PDF. No, because you can't see it.
फोल्डर बना के ना उसी में पढ़ लो तो
कौन सा डिस्ट्रीब्यूशन है? कौन सा डिस्ट्रीब्यूशन है? एक्सपोनेंशियल।
You can break it into two.
Oh.
इंडिपेंडेंट ऑफ के लिए लैम्डा की वैल्यू हो गया ना, वो तो क्या किया है लैम्डा की वैल्यू कैसे बनाए 0.5
मल्टीप्लाई भी तो करिए
यहाँ पर इससे पहले लैम्डा को मल्टीप्लाई कर दिया।
हाँ इससे पहले
और यहाँ पे रैंडम जनरेट करेंगे।
कंप्यूट टाइम में डालेंगे, कंप्यूट टाइम इज इक्वल टू टी हो जाएगा।
क्या भी पता रैंडम जनरेट कर लेना है ना, ये जो कैलकुलेट करके आया इसमें हम रैंडम नंबर को ऐड करेंगे। क्या करता
रैंडम जनरेट भी होगा ना तो
जो टी कंप्यूट टाइम मल्टीप्लाई हो रहा है ना, नेक्स्ट के लिए टी उसमें वो लेंगे, इनिशियल टाइम में तो टी इक्वल टू 0 ले लिया, ठीक है। नेक्स्ट उसके लिए टी जो है ना कंप्यूट टाइम रैंडम यूज करेगी।
Random number कितने किसके 0.1 टास्क है 1 से 2 1 से 2 के बीच में ना
Yeah, it can be predicted. So can we not
send or not also
alpha was close to 1. He says that he is one of them.
kind of PDF
Almost. Because when someone runs VM, you will determine that I use this VM for this amount of funds. About time. See this VM, how much time it will run. We have to predict and ignore.
बनाए कंप्लीट टाइम में रैंडम नंबर ये 1 आउट हो जाता है
तब मीन 0 लीजिए ना 0 1 इनिशियली 0 हो गया कंप्यूट टाइम उसके बाद ये चेंज करके 0 में ऐड करता रहेगा रैंडम नंबर में
कंप्यूट टाइम में अच्छा कंप्यूट टाइम में ही ऐड करना होगा ना
नहीं कंप्यूट टाइम में नहीं ऐड करना कंप्यूट टाइम तो किसी भी दिएगा रैंडम नंबर आपने रैंडम नंबर किया कंप्यूट टाइम यहाँ पास कर दिया है बस वही
For 1 month,
हो गया
for 10 hours.
ये रैंडम नंबर चले
Yeah, and when it's not working.
अरे आप थोड़ी Deakin चूज
हिंट दिया है ना तो 1 2 ही लेगा